So this section, as I said, is one of those little pieces of something bigger. There's a lot in this section that is not something you need to know specifically, but conceptually, yes. There will absolutely be some questions about differential equations on the exam. Absolutely. And typically, something that comes out of 10.3, which is what's called separable differential equations, is almost always one of the questions on the free response. So it's a big chunk of it. And the way they score the rubric on that one is if you don't recognize that it's what's called a separable differential equation, if you don't recognize that, you get 0 out of 6 points right off the top. Total of 9 points, but if you don't recognize that particular topic, you lost 6 of the 9. And so we're not talking about that yet today, but kind of introducing the notion. Now, within this, we're going to do a lot of talking about mathematical models. And we're going to use this concept of what's called differential equation to model a variety of things. So I'm going to show you a couple of little different examples, none of which you necessarily need to know specifically, but in the AP curriculum it says various applications of the derivative. And so these are going to be kind of various applications of the derivative, none of which you need to know specifically, but more generically, and be able to recognize that. And then beyond that, in a bigger realm, I don't know what kind of field of science or math or whatever you may get into, but just kind of the recognition that these things show up in a variety of different places. So, let's talk about the models. Now, when you think about a mathematical model, when you think about models in general, you may think about this. I would prefer you to think about this. Thank you. Thank you very much. Okay. That's my April Fool's joke of the day. A differential equation. This concept, this phrase, is really kind of a simple thing. It just simply means you have some kind of an equation, right? I mean, it's an equation. You got some kind of equation with some unknown function and some of its derivatives. This would be a differential equation. It's an equation that's got some function, y, and a derivative of y. There you go. One of the things that we're going to do in this section is talk about a solution to a differential equation. If I gave you this equation, you should be able to figure out with a little bit of work that the answer is 2. Because when you plug 2 into this equation, it works. And so one of the things, not quite yet, but one of the things we're going to get towards is, if I have a differential equation, finding a solution for that differential equation. Now in this section, we're just going to be given the solution. Like if I said to you, show to me that 2 is a solution to this equation, you would take 2, plug it in, and get 5 equals 5. Woo! And back in pre-algebra days, that's kind of the level of math you were doing. We're doing the same thing here. I'm going to give you some function y, and you got to figure out, is it a solution to that equation? Doing the exact same thing you did back here. So, a little quick reminder of something. Don't write this down. Just kind of go, oh yeah. Remember the concept of direct variation? Direct variation, y equals kx. This is just simply saying that the y varies directly as x. If x gets big, y gets big. If x gets small, y gets small. That's direct variation. Y equals 5x is a direct variation. Tuck that in the back of your head. So, talked about models, right? Keep it covered because the rippling chest. Anyway, thank you. One model of growth for population assumes that the growth of a population is proportional to the size of the population. The growth of the population. So the rate of change of the population is proportional to the size of the population. The amount of growth you're going to get is proportional to the size of the population. In other words, the bigger the population, the faster it grows. The smaller the population, the slower it grows. Think about this kind of an example. If I had one little cell in a little petri dish with lots of whatever cells need to grow, and it doubles, now I have 2. Not a lot of growth, right? Only added 1 more, so the growth was just +1 in that case. But if I had 1 million of them in there and they all split, now I've got 2 million. Which is a very different kind of growth. Even though it's still kind of the same, but the larger the population, the more growth you have, right? That's what that's getting at. All right, tuck in the back of your head. We're going to let, for this model, we're going to let T be time. We're going to let P be the number of individuals in a population, whether we're talking about people or bacteria in a dish or moose on an island. So, and again, this is not a specific example that you have to have, like, I got to make sure I get this down. Like, you need to know that the derivative of the sine is the cosine. This is not a specific example you have to have down. This is just an application of. So, right, to do this, we're going to let time be the independent variable, which is normally the x value. We're going to let p be the dependent variable. So, if I'm talking about a population growing, I'm going to say, after 20 years, what's the answer? What's the population grown to? Well, what I'm looking for is a rate of growth. Remember that sentence? What it said? Let me back up a couple of slides here. It says that it assumes that the growth is the rate of change of the population. So that's why I've got dp dt. So I've got the population, and then I'm taking the derivative of that population with respect to time. dp dt. And it was proportional to its size. So the rate of change of the population is proportional to the size. Another way of writing that, of course, is like that. And the aha here of connecting two thoughts together was, this is a differential equation. Because it's an equation, it's got a function and some derivative of its function in there. That's a differential equation. So, we have an equation that will work really well with that. Oh, forgot about this. So the rate of growth is proportional to its size, right? That's what this is saying. This is rate of growth, and it's proportional to its size. And an equation we have that fits that model is this guy. Remember, derivative of e to the t is e to the t, but the derivative of e to the kt is k e to the kt. And so that's proportional to the original function. The derivative is proportional to the original function. And so, well, let me remind you of this. When time 0, if I'm talking about the beginning of, I look at some population. In my petri dish thing, I put in 1 cell. So at time 0, my initial value is 1 in that little made-up example. So at time 0, when I put in 0, k times 0, of course, is 0, and e to the 0, of course, is 1. And so this value, which it could be sometimes just done as c, we did it last year as n sub 0 for the number at time 0, but that's the initial value. That's the initial population at time 0, that constant down front. And we're not going to have negative populations. So, this, let me back up, sorry. This model works really, really well in, let me say it differently, sorry. This equation works really, really well for that model, where the model was that the rate of growth of the population is proportional to its size. The bigger the population, the faster the growth. Now, that idea works really, really well, except in real life. In real life, that doesn't work so well. Always. It works well when the population is small, but for larger populations, it doesn't work so well. Now, this is kind of a, again, this is not a major component of AP Calculus you're going to see on the exam. But if you get into, I've taught this concept at, when I've taught some calc courses at UC, they're applied calculus, you'll see this in an applied calculus concept or course, because the reality of the population is populations can't grow unrestricted in most situations. And here's an example of what I mean. Anybody ever heard of Isle Royale? Have you ever been? I'm going to go this summer. I know, I'm really excited about it. Did you camp and stuff? Or okay, we're going to go and actually just stay at a small lodge. We're actually going to stay at the lodge for this first time, but I've never been. I went to a camp in Upper Michigan, and one of the trips we could have done when I was back when I was in high school was to go out to Isle Royale, but I didn't go for, I don't know why, but didn't. So I've always wanted to go, and so we're going to go this summer. Why not? All right, so it's an island. I don't know if you can see it here. So here's Lake Superior up here, and many, many, many years ago, a population of moose got out onto the island. And I don't know, a couple of them, but they were kind of out there all by themselves, and so without any predators to kind of keep things level, the population just kept growing and kept growing. Well, eventually what happened was, because it's an island, there's only literally so much food, and they kind of like ate the what do I want to say? The plants. Vegetation, that was the word I was looking for. Right? And so what happens in that kind of a situation is you get something that kind of goes like this, where the population starts increasing really fast, but then if it gets too big, it starts to level out. So it'll grow and then start to level out. And it reaches some kind of maximum value. Now, sometime later, a population of wolves got out there, and then that helped to keep the population of the moose down at a lower level. Because the wolves, we eat the sick and older moose and keep the population kind of level. Recently, I read an article about how there was like one dominant male wolf, and so the population kind of became a little inbred, and then so they were having some issues with getting new wolves because whatever. So they just recently imported a couple breeding pairs to try to help that population stay a little stronger. Because without the wolves, the moose population is getting too big, and they're overeating and they're starving and in the winter and whatnot. So it's a fascinating, if you do any sort of biology things, or I don't know what field would study it, but they look a lot at the predator-prey relationships, specifically on Isle Royale between the moose and the wolves, and it's a fascinating kind of thing. But go do a Google map sometime, because you don't get any sense of what the island looks like from this picture, but it's a really cool-looking island. So, what you're going to see out there is something that looks like this. What happens is, if the moose were truly left unrestricted, they would not simply grow forever. Remember what e to the x looks like, right? E to the x looks like this. Unbounded growth. But you can't put 1 billion moose on that island. It simply couldn't handle the population. And so what you get is some kind of maximum value, which is what's called the carrying capacity. So I'm going to totally make up a number. Let's say 200 moose is like the most that this island can handle well, and still be able for the vegetation to regenerate each year and the moose to not be sick and die off. And so you're going to get a graph that looks like this. And a lot of things behave that way in the real world. So remember what I said about this equation being a good model, but only for small populations? Because it can't just continue to grow infinitely. Just doesn't work. There's only so much room. So look at this equation. The K in this equation is that carrying capacity. There's a certain capacity that you'll run into for whatever it is you're talking about. the Earth has a carrying capacity of people. There's only at some point, there's only so many people we can have on the Earth and still be able to live. And that will become a thing that world leaders need to deal with at some point. But look what happens as the population gets bigger. As the population approaches this number, look what happens to that. As the let me make up that number. I'm going to put 200 in. So as the population approaches 200, this becomes equal to 1. And then 1 minus 1 is 0. And then what you get over here is this becomes times 0, and you get 0, and the rate of growth is 0. So as the population approaches the carrying capacity, the rate of growth of the population approaches 0. So when the population is small, on the other hand, so when this is near 0, then this is near 0, and then this becomes just k times p times 1. And so then you get that equation, which is what I said works well when the population is small. And as the population approaches, right, as this gets closer to 200 and this is closer to 100 or whatever the carrying capacity is, this becomes close to 1, and then you get 1 minus 1, and you get 0 growth. We don't do a ton with this equation, but you're going to see it a little bit in, let me see if I still have those up here. I think so. So this is just, I just typed in logistics growth. Oh, let me mention that. I kind of skimmed past that page. Let me go back to that real fast. This is what's known as a logistic differential equation. You'll see that vocab. That is not something you need to know right now. It'll come up potentially in a college course sometime. So tuck it in the back of your head maybe somewhere. Logistical growth. But so I just typed that into a search and got all these different kinds of equations. So sometimes the growth is going to happen real slowly over time. Sometimes it can happen, you'll reach that carrying capacity really, really quickly, depending upon what's going on. And you can also have it decreasing too over time. There's another one here. So this equation, take those out of there. Again, just type that in. But this is exactly the equation I just gave you. Now, instead of using P right here, they're using N. But that's exactly what we just had. So the rate of change of N is R times N. But as N approaches K, that approaches 1, and then this would approach 0. And that's the exact same equation we just had. Again, you don't need to have that off the top of your head. That's not something we're doing. But recognize it as a differential equation because it's got the derivative. This is the derivative of some function, and there's the function there. So the rate of growth is proportional to the size of the population. Tuck that in the back of your head somewhere. All right, talked about all that. Yep, 0 growth. All right. New concept, Roman numeral 2. Again, what's the word I'm looking for? Various applications of the derivative. A model for spring motion. You remember old Hooke's Law. Now, we did stuff with Hooke's Law when we were doing work. Similar-ish idea with this. So if a string is stretched or compressed, x units from its natural length, then the force it exerts while you're holding it there, not moving it, I'm not talking about work and moving it, is proportional to x. The farther you move it, the more force is required to hold it there. Right? The farther you stretch it and you hold it, the more force is required to keep it in that position. again, this notion of proportionality to the function. Now, in this section, they do this what's called this restoring force. So if I pull it one way, the spring is trying to restore it the other way. And so you can think of it as a negative force, or a force in the opposite direction. So they do this. They stick this negative in there to give it that that idea of restoring it back to its original position. Oh yeah, you say. Oh yeah. Force is mass times acceleration. And mass times acceleration, well, acceleration is a second derivative. And so that equation then becomes this. Now remember, let me remind you about this notation. This will come up again and again. You will see this almost guaranteed on the AP exam. You need to understand what it means. So let me show you that, what that means, and I'll come back to it in a second. If I had some function, and I wanted to take the derivative of that function, I could do a prime notation, but we also can go d dx. Now normally we say dy dx, but I could say d dx of y, the derivative of y. If I wanted to take a second derivative of that, I would go like this. And so, the reason that the 2's, let me back up a second, the reason that the 2's are where they are in that equation is because of how this works. I am not squaring d. That is not what's going on. You've got to recognize this as the derivative, and the 2 just simply means the second derivative. And the reason that the 2 goes here is because I've only got one y, but I've got two d's. So they write that. That just simply means this. Stick that in your head. Absolutely, you will see that on the AP exam somewhere. They'll use that notation. And you just got to recognize that means the second derivative of y. That's all it means. Okay? So, back to this. Hooke's law, then, mass times acceleration, is equal to, well, it's proportional to the distance that you're holding it, and the negative because of that restoring force in the opposite direction. So then what they do, you'll see this in the book, then they take this m and simply divide both sides by m, and that's how this m ends up in the denominator down over here. So look, I have a differential equation. What makes it a differential equation is it's an equation with some function and one or more of its derivatives. In this case, it's the second derivative. So, second derivative is proportional to x, but has the opposite sign. Can you think of a function whose second derivative is proportional to the original equation, but with an opposite sign? Yeah, but I'm looking. Yes, but I'm looking for. Yes, but I'm looking for a specific equation. The sine or the cosine. So if I take. So we know the function whose second derivative is opposite of itself, right? So if I take the sine, derivative of sine is the cosine, but the derivative of the cosine, or the second derivative, is the negative sine. And so, remember the whole premise here is finding the models that fit this. So a model, a function that will model this for us, is going to be the sine function. And oh, by golly, it kind of looks like a spring too. Huh. Just like a spring. All right, tuck that in the back of your head. Again, not something, they're not going to specifically ask you a question about Hooke's law, probably. This is more along the line of what you will probably see. That's a differential equation. what makes that a differential equation is it's got some function and one or more of its derivatives. Yes, sir?
On the test,
yeah.
They like using like the prime signal or like the DS?
Both. They'll do both. So you just kind of be comfortable with either. Now, vocabulary. What I just showed you there, that's what's called a first-order differential equation. Sounds really impressive. But all it is some equation where you have a function and one or more of its derivatives. That's a first order. So it's just you name them by the highest derivative that's in the problem. So on that last one I just had, that was a first order because the highest the highest derivative in there was a first derivative. Let me back up for a second. This would be a second order. Ooh, look at that. Because you got a second derivative in the problem somewhere. So it's kind of like when, what's the degree of a polynomial? The degree of the polynomial is always the highest power. Same kind of logic here for this. Forget what equation I gave you before. But the question now is about finding a solution to a differential equation. Now, as it turns out, in this particular section, usually what they do is just give you the solution and say, prove that it is. So if I gave you this equation and said to you, prove that x equals 2 is a solution, back in pre-algebra days, you would go 2 plus 3 equals 5, and write 5 equals 5, and you go, yep, and smiley face, and there you go. So when you prove something is a solution, you plug it in and show that it works. That's exactly what you're doing here. You're proving that this thing given to you is a solution. Don't write this down. But I wanted to show you kind of the hardest level of problem that they give you in the homework, because mostly what this is about is algebra. So here is an equation. This is a differential equation. It's a differential equation because it's got a function and one or more of its derivatives. So to find a solution to that, I'd have to do a bunch of work, and we don't know how to do that yet. So they gave me the solution. Here you go. Here's the solution. Prove that it's the solution. And to prove that it's the solution, you just simply take it and plug it in, right? And that's exactly what you have to do here. Except I have to plug in y. Well, here's y. It's going to go right there. But over here, I have to plug in y prime. So, step one, before I do any plugging, I got to figure out what y prime is, because that's what has to go into this one. So I'm going to take this equation and find y prime. Again, don't write this down. This is just, you don't need to, the arithmetic here is kind of irrelevant. I'm going to guess that some of you could get lost in this arithmetic, and you should be able to do this arithmetic, but that's not the purpose of this conversation. But let me walk you through it just to kind of remind you. So, find y prime. In order to find a derivative of a quotient, I got to do the quotient rule. So, derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all over the denominator squared. Do a little distributive property. C e to the t times 1, of course, is just c e to the t. C e to the t times c e to the t is c squared e to the 2t. Because when you multiply numbers that have the same base, you add their exponents. So e to the t times e to the t, add the exponents, and that's where you get 2t. Likewise over here, distribute this guy, but don't forget you got a negative sign here that's going to change them both into plus. Ooh, you say? Thank you. Look what happens there. They cancel. And so finally, all of that was just to figure out what y prime is. So I haven't checked to see if the original equation was a solution yet because I had to know what y prime was. So now I'm going to come back to that. Here's that differential equation, that 1/2, whatever it was, problem. Now I'm going to plug in y prime and the original y into this. So y prime's coming in here, and the original y goes in there. And if I've done this correctly, this right-hand side should become equal to, remember this is y prime, the right-hand side should become equal to that, because that's what's on the left here is y prime, right? So all I need to do is see, does that become, back up a slide, equal to that? That's what y prime is. So whack away, here we go. 1/2. So I'm plugging y into here. I've got y prime plugged into there. I got to see if this is equal to that. Now remember last year when we did those trigonometric proofs where you had some really big nasty trig thing and I had to prove it was equal to sine of x. You had to do all this stuff and wacko. They were equal. We were told they were equal. But the question was, prove it. And so you had to walk me through all of the steps. So if you have a problem like this, you can't just say, hey, yeah, this is equal to that. They are. I know they are. They're telling you this is the solution. Just show me that it is. And so you got to walk me through all of the algebra to get there. So here we go. How do you square a fraction? Numerator squared, denominator squared. Now notice, as I'm glancing over here, this denominator is 1 minus c e to the t squared. Well, that's what I got right here. So I didn't actually want to square that because I knew that's what I was trying to get in the denominator, and now I've got it. But I did square the numerator, FOILed it. And c e to the t squared is c squared e to the 2t. But now I got to subtract 1 from that thing. So to subtract, I've got to have common denominators. So I rewrote 1 like that. Oh, there it goes. And so minus 1 minus c e to the t minus 1, and then I squared that because that's what it says to do. Then I left the denominator the same because I had common denominators. So look at this one and that one. They go away. But minus minus, this is going to become 4. And then this guy and this guy, because of this subtraction sign, cancel out. Ha-ha, you say. That's exactly what I had on the left-hand side, way back up there at the top somewhere, right? A few slides ago. That's what the y prime on the left-hand side said. And so what I've done is proven that the equation they gave me was a solution. Let me back up a few slides to the very beginning. I had to take and show that when I plugged this into here for y and the derivative of this into y prime, that these two sides became equal. And they did. And I can see all the algebra that walks me through to get you to that point. So much like the proofs we did last year with the trig, at the very bottom, the one side or the other, or depending on how the equation's written, you need to have a true sentence. Getting there, getting there, getting there. All right, part B of this. So I just showed that that equation given was a solution. But sometimes they have what's called an initial condition. Remember in that problem there were some c's, there was t, that was the independent variable, but then there were these constants, c. And there's lots of variations on the theme. This is one kind of version of it. What they wanted to do is say, okay, if I plug 0 in for t, make it so that that equation is equal to 2. That's what that says. If you plug 0 in for t, remember t was the variable in this problem. If you plug t in, 0 for t, make the answer 2. So I'm going to take that initial problem. Here's what I said was the initial value. This statement right here says if you put 0 in for t, that's a 0, sorry, go away. If that's a 0, you're going to get an answer of 2. So plug in 0 for t? Well, if t is 0, e to the t is 1, and this becomes 1 plus c over 1 minus c. So I plugged in 0, and I'm getting 2 as an answer. What I'm doing is finding not a general or a generic solution. I'm finding a specific solution that will work in that differential equation and give me an answer of 2 when I plug in 0. How come? They just want a specific one, not a generic one. And so when I solve this blue equation, I get 1/3. So the way they might word this is, show that, remember it said y equals, what was it, 1 plus c e to the t over 1 minus c e to the t. That's a general solution. But then they might say, find the specific solution such that y of 0 equals 2. And so, now that I know c is 1/3, I can plug back into that original equation. I can plug in what I need to for the value of c. And that's a specific solution to that differential equation that gives me this initial condition. Now, vocabulary there, by the way. The initial condition means times 0. So when t is 0, I want the answer to be 2. I'll do one with you. This is the kind of question you see out of homework. In fact, this is from the homework. This is a differential equation because it's got some function and one or more of its derivatives. Show that this is a solution. Which means when I plug this in here for y and then plug in the derivative of that into there, it should give me a true sentence. Well, step 1, what's the derivative of that thing? Right? Because this, of course, right, multiply down, subtract 1, that's where the negative 2 comes from. And so now simply plug those two. So here's y prime. There's y prime. Back up a slide. Here's y. Just plug them in for y and y prime. And see if it works. So here's the y prime plugged in. Here's the y plugged in. Distribute. Aha! Aha what? There they go. So what I said to you a little bit ago was, when you're doing this, proving that it's a solution, when you plug, remember when I did the x plus 3 equals 5, when we plugged in 2, I got 5 equals 5. So at the bottom of this, you should have some true sentence. That's it. In this section, they're going to give you the solutions. In in 10.3, section 3, we're going to find our own. And that's what I was talking about at the beginning, about separable differential equations, where you have to be able to find the thing that works. But not here, not yet. Really the end.